Okay, good morning. It must be Monday. What I would like to do today, here's a brief summary of what I'd like to cover in today's session, is we want to wrap up the financial modeling work that we did last session. And what I want to point out to you is this formula for the future value in terms of compound growth is very important for you to remember. And this is, let me just ask you a question. What's P stand for? What's it mean? The principal, or also called the present value, or the initial value of an investment. A is the future value as time passes. This is a function, A is a function of time in years, typically for this model. Very important for you to remember this. How many of you remember it? How many don't yet? Don't know it yet? Okay, you got to get it in your brain. It's like your phone number. Make sure you know it, okay? Somebody else now, tell me what R is. What? Well, something a little more descriptive than just rate.
Interest rate.
Interest rate, but
Rate of change.
annual percentage rate. Annual percentage rate. That's the rate of return for the investment over the course of a year, okay, if there was no compounding. Now somebody else who hasn't spoken up yet, tell me what N is.
Number of times it's multiplied the year.
Number of times, as Jerome said, the number of times you're getting the interest given to you per year. So this is the number of compoundings per year. So, and then T represents what? Time in
Years.
In years. Time in years. So if you look up here at this formula, and you're starting to develop some ability to look at a formula and actually have a sense of what it's all about. And a lot of you had some real trouble at the beginning of the term, even with basic algebra things, of trying to make that connection between looking at a formula and understanding its behavior, its characteristics, and that kind of stuff. So you folks have actually come a long way since then. Now, up here in the exponent, the product of N and T, that means the number of compoundings per year times the number of years. So that's the total number of compoundings that are going to occur to reach a point sometime in the future, like 2.5 years, 5 years, 10 years, something like that, times the number of compoundings. That's the total number of compoundings. For instance, if you bought a house, now this is more of an investment model here, but if you bought a house where you took out a loan and you're paying that loan off, like say a 15-year fixed mortgage, you're making monthly payments, 15 years times 12 would be the exponent in there. 15 times 12. That is a lot of payments to pay off that loan for the house.
Is there a different model?
Oh, yeah.
For
Yeah.
loans? Okay.
Yeah, for loans, yeah. This is more of an investment model here, and we would use this for simple compounding kinds of things. Okay. And it's not much more, there's no more sophisticated math to understand like a mortgage or a car loan, that kind of a thing, than really understanding this. You folks are capable of it. We're just not teaching it as part of this course. You can look in just about any algebra book, though, and find those kind of formulas and be able to understand them. Okay, so that was compounding. Now, in the last session, we did some problems, and we left off a problem where I think we had monthly compounding, and I want to pick up and finish that problem off today. And then we'll do some other things. I also, in the last session, talked about this model, PERT, P-E to the R-T, is equal to the future value. And so this is for what type of situation? Somebody else who hadn't spoken yet. What are we going to use this one for?
Exponential growth.
It is exponential. All of these are exponential growth. Both of these are exponential growth. But this is for continuous compounding. The compounding is occurring continuously. And we went through a little exercise in the last session to illustrate why. Okay, how this turns into that situation. Okay, so what we're going to do is we're going to wrap up that financial model with an example that we didn't quite finish on the last session. And then what we want to spend the rest of the time today talking about, there's no real new mathematics here in these two. This is called growth. There's another section in our book dealing with growth models. This could be population growth oftentimes, or as we spoke of previously, bacteria colony growth, that type of thing. It's called uninhibited growth. There's nothing interfering with the growth occurring, and you should be good enough to be able to look at this formula and see the y-intercept is up at a naught. That's your y-intercept. And then it's going to grow with a base e exponential raised to the exponent of k, which is the growth rate times time. Notice in the book, in a textbook, the decay model is written exactly the same way. I usually don't do it this way. I usually put a negative up here with the exponent because it's real clear to me, and it's clear to you as well, if you have a negative exponent, you're going to have a decay model as long as the base is bigger than 1. And E, you know, is about what? 2.718 approximately. Try to keep that in your head as well. So notice what we have here. In this model, both models are identical in the book, except for the growth model has a k value up here, which is greater than 0, positive. And on the decay model here, the k is less than 0, negative. So this is going to be a decaying exponential. And then we'll talk a little bit, if we have time, at the end of class about a logistics model. At least give you the sense of the curvature, the kind of behavior that occurs on this thing, the shape of the curve. And you'll be able to understand why that's quite useful as well. So the problem we left off with in the last session, I'd like to begin there, was the following. I believe we had an $800 investment. We had $800. No, actually, I think that was actually a future value at 3.5 years. Right? So A at 3.5 years was equal to $800. Remember, we wanted to have this much money in the future. And our interest rate, our annual percentage rate, called the APR, happens to be 7%, which we know is 0.07 as a decimal. And the time was locked in at 3.5 years. Okay, without going through all of that work, we ended up with the present value. By dropping these into the compound interest formula, we ended up with the 800 being equal to the present value, or the initial value, times 1 plus 0.07 divided by 12. Oh, we're doing also, I believe, monthly compounding here.
Yeah.
So we have to have n equal to 12 times per year. And this is raised to the exponent then of 12 times 3.5. Okay, when we solved this for p, in other words, this arithmetic over here is just a number, and we divide both sides by that number and solve for p, we ended up with a p-value of 626.62. So this much money must be invested so that in 3.5 years we end up with $800. And here's what we also had. This is the amount of money in the future versus time in years. And so we ended up here, we actually had a point out here where this was 800 at 3.5 years. So that was the point we were given. And we knew the interest rate. So what we did essentially is we built a model, given this data point, we built a model that figured out what this initial value was, which turned out to be 626.62 at time 0. So that in 3.5 years you end up with the 800. So that was the problem we tackled on during the last session. Now the question is, this model continues to grow then. And so what I'd be interested in is how much time would it take for this amount of money, the original amount, to double. So this is going to be the doubling time. And I'm going to label that T sub D. And so what's going to happen is we want to end up here where we are at a height here, a height of doubling this value, doubling the initial value. Okay? So how would we do the math? How would we do the math to figure that out? We want to figure out this doubling time, this height right here, this amount of money.
Wouldn't you use, instead of putting 3.5 in for T, you'd just put T there?
Doesn't this have to turn in to be $1,253 and 24 cents?
Yeah.
So we're trying to get up to that level. And as Melissa said, what'd you just suggest? Pass that back to Jerome.
In the formula, putting just T instead of 3.5 and solving for T.
Okay.
2B equals BE.
Okay.
T.
Okay, here, tell you, let me just put it up here. I think what you folks are saying is correct. We're looking for the future value. Now here's our model. What we're trying to do is double the initial amount here. So we want this value to be this 1253.24, and we started out with 626 after we did this initial problem, first problem, 62. And then we had numbers going in here, 1 plus 0.07 divided by 12 raised to the 12. And then now, look at my exponent up here. What do I need to put for T? Look at the picture here. I'm letting my future value be 1253.24. Initial value this. Everything's all numbers. So what needs to go up in that exponent right up there?
T. TD.
T sub D. T with a subscript D for the doubling time. Now look at the math. Everything is numbers here except that T sub D. What kind of an equation is this?
Exponential.
Why is it called an exponential equation? Very good, because it has an unknown in the exponent, as we said about 1,000 times this term, right? So what we have to do is just simply isolate this mess, isolate this, so that that T sub D is sitting there as an exponent on this base. And what happens if I start by dividing both sides by 626.62?
You get 2.
Yeah, we're going to end up with 2 here, aren't we? Okay. So we're just going to end up with 2 equals this thing with the exponent. Right? And would it matter if this problem had been $800 in the future, 3.5 years, and we did this stuff and ended up with these numbers, or could it have been any numbers? Could have been any numbers, couldn't it? So the kind of problem we're tackling here is using the compound interest formula for a general situation where this future value here is twice the initial value. So you're always going to end up with a 2 right here if you're doing a doubling time problem times this base. Okay? Now, what I want to do is punch up, and we did this the other day, and actually it's on your this paper that Jerome lent me a moment ago. We punched this number up in the last class session. Look at your note there, Jerome, your notes from class. This number we punched up, and it was 1.07, what? It's down there near the bottom of your paper.
1.2767.
1.07.
2767.
2767 raised to the T sub D.
Sorry. Erase the 0 and the 7 after the period.
No, no, you wrote it down wrong.
There's one that
Or
says
did I?
1
Oh, there it is. 1.0723.
2,
There
3,
we go.
Is
round.
that the one you're looking for?
That's what I got just
Yeah,
now.
0723.
Or
Yeah.
2290081.
Okay, if you're watching the DVD and you've got your calculator, just punch this thing out up, including that 12, and you should get this number. And then that exponent t sub d is still there. Okay, this thing, when you divide by the initial amount, you end up with 2. So what I'm going to do is let's come down here on the board. Sorry for these small boards like this. But what we end up having is a simple exponential situation. And this is equal to 2. Now you need to use what to solve these things?
Lots.
Logarithms, as we've been studying over and over again. So what we do now is take the logarithm, and you can use whichever button, whichever base log you happen to use off your calculator. Base what or what? You have 2 of them.
Log, base 10 or e.
Base 10 or e, right? So if you use either one of those, you'll get this. Why don't we use base e just for the fun of it? So if we take the natural log of both sides, and you've been doing this now for over a week, hopefully.
Over a week. And that's a long time.
Yeah. And then we now have the natural log of both sides of the equation we've applied to both sides of the equation, and the exponent now by the power rule pops out in front. And so the t sub d comes out in front. And then we're going to move the natural log of 1.0723, divide both sides by it, and it's going to end up over through division underneath the natural log of 2. So what I want to write down for just a second is that. Now, what I'd like you all to do is to punch the natural log of 2 on your calculator. 0.6931 approximately, and then the natural log of 1.07 should be a number very close to, think about it, the natural log of 1 is the exponent of e that gives you a number very close to 1. So that number has to be pretty small, doesn't it? What'd you get?
0.067.
One more.
7.
Okay. Okay, and then finally, the division of the 2 is going to give us our doubling time. Okay, about 10.23. And this model, remember, look back at the original problem. The modeling in time is in years, so this indicates that the investment, this initial $626 investment, or any investment, compounded monthly at 7% annual percentage rate, any investment will double in 10.23 years. $10.23 years. Now, I mentioned something a couple weeks ago in class when we first started talking about logarithms called the rule of 70 that real estate people and investment folks use all the time. What it is it's a rough estimate for doubling time, and it is 70 divided by the annual percentage rate. Think about it. If you took this investment at 7%, and you take 70 divided by 7, you get 10. While property values were growing in the last few decades, realtors were using this all the time to try to get you to buy a house from them. Okay? They would say, you can buy this place for this much money, and in about 10 years, if the rate of return was about 7% on the growth of the investment, that you're going to double your money in about 10 years on that investment. And oftentimes homes were growing at a much more rapid rate, like say 20% in certain parts of the country. So if you'd bought a place at 20, growth rate occurring at 20%, folks, 70 divided by 20 is
3.5.
3.5. You would double your investment in 3.5 years. Turn around, sell it. A lot of people did that, and then a lot of people got in trouble also once that bubble burst. Okay, so remember this rule. It's a good rough estimate. Look at that. We're only about a quarter year off. We're only about a quarter year off by just using that rule of thumb. And do you see why it's called the rule of 70? That's the reason I wanted you to punch this natural log of 2, 0.69. Okay, so that's the idea that you'll find useful in the future. Okay, any questions about that? It's very practical material here in one quick example, and then some generalization about doubling time. Okay, again, the process was you just start playing with it and you see where it gets you, and notice that we ended up with an exponential equation in here, and then your technique that you need to remember when you see an exponential equation is to isolate the exponential, which is what we did, this thing involving the exponent. We isolated it, and then we applied logarithms because that power rule is very handy in being able to solve for the unknown exponent. Questions? Okay.